So we're recording already?
Yeah,
Oh,
it's
okay.
So maybe we can get started. Hello, everyone. Welcome. Today, we're very happy to have Irene Valenzuela from Harvard University speaking about nothing is certain in string compactifications. And also, Irene will be lecturing at the school, which starts next week. And you can see the webpage for information about that. Thank you, Irene.
Okay. Thank you very much. Thank you very much for the invitation to give a seminar in this online series of QFT and geometry. So I'm going to talk about a recent work in collaboration with Iñaki García Echevarría, Miguel Montero, and Kepa Sousa, which is based in this recent paper in arXiv. So the question that drives our work was if any non-supersymmetric vacuum is always unstable. So of course we know that once we break supersymmetry, typically there are instabilities, but can we ensure, I don't know, can we ensure that this will always happen? Can we ever find some universal instability that will always be there once supersymmetry is broken? And regarding this topic, there was a Swampland conjecture a few years ago claiming that indeed any non-supersymmetric vacuum is unstable. And this was based on a sharpening of the weak gravity conjecture, which was providing a decay mode in the case in which the vacuum was supported by fluxes, because then you could have a bubble instability and the tension of the wall of the bubble was smaller than the charge, so it was going to expand and mediate an instability. But I mean, you can ask, for example, what happens if there are no fluxes, or maybe for some reason I cannot apply this bubble instability. So in the quest of finding some universal instability, we end up working with bubbles of nothing. Okay, so this talk is about bubbles of nothing and how they are far more common than what we thought, at least if there are extra dimensions. I mean, if our vacuum has some compactified extra dimensions. So I'm going to explain in more detail what the bubble of nothing is and review everything to make sure that we are all in the same page. But before that, let me just simply say that a bubble of nothing is a non-perturbative instability in which a bubble pops in space-time and starts expanding at the speed of light, and there is nothing inside the bubble. So it describes an instability from the vacuum to nothing. So this is what my talk is about, but nothing is more important than to ask questions. So please, if you have any question, just interrupt me at any point. I would be happy to answer. Okay, so this is the outline of the talk. I'm going to review first what are the bubbles of nothing, I mean the original construction of Witten, and then I'm going to discuss what are the possible obstructions that we have, that we can have to avoid the presence of these bubbles. No? So there's a topological obstruction, which I will discuss how to understand it in terms of Bordism group. And then there is a dynamical obstruction that we'll see is related to some local energy condition. Once we understand this, I will use it to generalize, to construct new types of bubble of nothing. In particular, we will construct bubbles of nothing even if the boundary conditions preserve supersymmetry, unlike with the Witten's bubble, as long as the vacuum itself breaks supersymmetry. So we will construct a bubble for T3 with supersymmetry preserving boundary conditions. And then I will explain how to generalize our constructions when we have more ingredients, we have fluxes and other things. And discuss how general is to have bubbles of nothing every time supersymmetry is broken. Okay, so let's start. So the bubble of nothing already appeared, well, it's a construction that appeared in this paper by Witten. And it was non-perturbative instability of the Kaluza-Klein vacuum when we were compactifying a circle. So this is the instanton solution. It's a perfectly well-defined solution to the Euclidean equation of motion of Einstein gravity. And if we rotate back to Lorentz, we can see that the end point of the decay, that is mediated by this instanton, looks at very large radius just as Minkowski, but it's not just Minkowski, it's Minkowski with a hole, because this instanton solution is only defined when this small r is bigger than capital R, which means that when we go back to space-time, it's only describing Minkowski when this small r, this radius, is bigger than R. So the space-time ends here. This is the bubble wall, and there is nothing inside. Still, even if this looks completely singular, and it's singular from a 4-dimensional point of view, from a 5-dimensional point of view, from the point of view of the full solution, is completely regular and non-singular and smooth. And that's because the size of the circle, of the internal, the compactified circle, is going to 0 when I'm approaching the wall of the bubble. Okay, so you can see that the size of the circle goes to 0, shrinks to 0 size, and this allows the full solution to be geodesically complete and smooth. So this is what I said. We have a circle, and we have this sort of geometry, that we have this cigar that is shrinking to 0 size at the wall of the bubble. So the topology of the solution is an S cube, so we have this sphere, times a disk, okay, because this radius times the circle times this radial direction. Since I can feel the circle and it's shrinking to a point, topologically it's as a disk. And we can compute the decay rate, and the decay rate is finite, and depends on what is the value of the radius of the circle at infinity. Okay, any question about this? Okay, so I just told you that there is a bubble of nothing. Maybe probably most of you, if not all, already know, but it's a bubble of nothing when we have an S1. So shall we worry about it? I mean, what does it mean? It means that every time we compactify, we have this bubble of nothing or not? And the point is that we can have a topological obstruction. So this was also already pointed out by Witten in the first paper, that if we have fermions, since the fermions pick a minus sign when we rotate by 2 pi, in order to be well defined in this disk, since the circle is going to shrink to 0, they need to have antiperiodic boundary conditions. Which means that the bubble will not exist if the fermions, if I have fermions in the theory that have periodic boundary conditions, which are precisely the boundary conditions that are consistent with supersymmetry. So the lesson that you might get from here is that the bubbles, these bubbles of nothing, in general, they do not arise in supersymmetric theories because of this topological obstruction, even if the vacuum later on breaks supersymmetry, because this is a topological obstruction, so even if you break supersymmetry spontaneously, that's not gonna change. So you should not worry about it, okay? It's fine. Okay, the message of my talk, what I want to explain, is that this lesson, this particular lesson is wrong. And that the bubbles can also be allowed even if we have periodic boundary conditions, as soon as we are more ingredients, like it's done also in this paper, that has some non-trivial Wilson lines, or as long as we just go to higher dimensions and we don't think simply of the circle. Okay, so how do I understand that this topological obstruction is absent, okay, even if there are periodic boundary conditions? So let's be more general. I mean, bubble of nothing is not necessarily for a circle. I mean, we can in fact generalize these bubbles to any compact manifold that shrinks to a point. So let's consider your favorite compactification. So this is your favorite compact manifold. And the message is that the bubble of nothing is going to exist, at least topologically, if this compact manifold can be shrunk to a point, right? So this is equivalent to say that this compact manifold can be written as the boundary of another manifold of 1 dimension more. And if we have fermions, we have a spin structure, then we need that this spin structure of C extends to B. Why is this? Well, if you look at the circle, I mean, the fact that this circle can be shrunk to a point is because I can feel the circle, right? The circle is the boundary of a disk. So more generally, I mean, we will have the same type of bubble of nothing geometry if this compact manifold can be filled in the sense that it's the boundary of another manifold of 1 dimension more. And that's why it can shrink to a point.
Irene, can I ask you a question before you?
Sure.
So this discussion of the stability in the supersymmetric case. So we know in supergravity, there are microstate solutions where you have circles that shrink where horizons would be, which are stable solutions with many, many bubbles around. And those are supersymmetric setups. How do those evade the statement that you're making?
Yeah, so I mean, it's a good question, and it should be bothering you that I'm saying that it's so trivial to have bubbles of nothing. But that's because I'm only talking about the topological obstruction. So I will discuss later that even if the topological obstruction is absent, we have to care about the dynamics. And it could be that the decay rate for the bubble, no, and for the instability is 0. So we need to take into account both things. But at the level of the topology, we just need that this compact manifold can be shrunk to a point. That's enough to have the bubble of nothing as a topological solution. Okay.
So you mean it matters which theory that you're looking at, because those theories, for example, have Chern-Simons interactions, which really what supports those bubbles.
It will matter once we talk about the dynamics. Yes.
Thank you.
The thing is that the topological, I mean, it's good to distinguish between the two types of obstruction. I'm starting with the topological one because the topological obstruction is more robust, right? Like then it doesn't matter how you break supersymmetry in the vacuum. I mean, the topological obstruction will always be there. But if the only thing you have is a dynamical obstruction, as it will happen in other cases, then in the moment in which you break supersymmetry, even if it's just by a little bit, it might be that the bubble of nothing exists. So that's why it's important to distinguish. But you are right. I will discuss what happens with the dynamics later on. Okay, so.
Since you've been interrupted, I have another question.
Yeah, of course.
Still at the topological level, what if there are fluxes on the...
Yes. So the thing is that right now I was just talking about fermions, right? So I just care about the spin structure that has to be extended to B. But then depending what structure I have, like for example, if I have fluxes, I have to take care of these fluxes. No? I need either to put some defect that it's the fluxes, or sometimes with Bianchi identities, it's enough with the geometry, in fact, to eat the flux, even if you don't have a UV defect. And this will appear now when I will discuss the Bordism group, because it depends what is the structure that you put here. I mean, so.
But so in the end, I would expect that it doesn't give rise to an obstruction, right? Because I can always say that there's a brane that acts as a source of the flux. So in other words, the bubble of nothing is really a brane.
In principle, yeah, you can expect that if you also include the brane, and that's why, I mean, Kumrun and Jake, in fact, has conjectured that this group will always be zero. But let me postpone it just a little bit because it's easy to explain it in terms of the Bordism group, what happens. But yeah. Okay, so at this level, I mean, you just need, the first requirement, the requirement that we need is that this compact manifold is the boundary of another one, and this is an answer, this is something that has been classified by the mathematicians, and the answer is that this compact manifold will be the boundary of another manifold if it belongs to the trivial class on this Bordism group. Okay. So why is this? Okay, so what is this Bordism group? So basically it's an equivalence relation. Maybe many of you already know because it's has been very useful in the context of anomalies. And the thing is just that if you have two manifolds, they are in the same Bordism class if their union is a boundary, right? So like you can see in this picture. And this forms an abelian group structure, and the trivial class of this group is a manifold which is a boundary by itself, okay, as our bubbles of nothing. So that's why a manifold can admit a bubble of nothing only if it belongs to the trivial class in this Bordism group. If I have some spin structure, then I have to check what is the spin Bordism group. More generally, if I have more other ingredients, what happens? Well, before that, what happens is that I have to change what is here, and this is what I will discuss later. Okay, but let's before adding more things, let's revisit the witness example with this in this language. Okay, that we just have fermions. So if we are in one dimension, okay, as the circle in Witten, one can check that the omega spin, omega 1 spin, is C2, which means that you have two classes, two Bordism classes. There is a trivial one, which is precisely, the one in which the circle has antiperiodic boundary conditions, and the other one with periodic boundary conditions. And that's why only the antiperiodic boundary conditions that belong to the trivial class is the one that admits a bubble of nothing solution. We can now go to 2 dimensions. And then again, omega 2 spin is C2. So it works the same way. All the manifolds belong to these 2 classes, which in the end are associated to antiperiodic and periodic boundary conditions. Now we can go to 3 dimensions, 3-dimensional manifold. And this is an example in which the physics induction sometimes fails. And maybe you would expect that it's again C2, or that at least C2 is a subgroup of it. But actually it's 0. Which means that any 3-dimensional manifold admits a bubble of nothing. If it has just some spin structure. Okay, so even if the manifold has supersymmetric preserving boundary conditions, there's no topological obstruction to have a bubble of nothing. Just because, this group is 0. So there is only one class, which is the trivial class. And not only that, we can go to higher dimensions. And in 4 dimensions is again non-zero, but in 5, 6, and 7 is 0 again. Which means that it's not only for 3-dimensional manifolds, but for example, M theory on G2, 10-dimensional string theory to 4 dimensions, any Calavillao, ADS compactification of 5 manifolds, all enter in this category here. As I will explain, it depends what ingredients you have, we might have to change it, but at the level of the string structure, these are 0. So, yeah, so now is the moment to change it. So that's what Alessandro was asking. Depending if I have sharp fermions, fluxes, and so on, I might need to add more things here, not just a spin structure, okay, in order to have this compatible. And at the end of the talk, the solution we're going to construct is enough to consider just spin structure, so that's why I'm focusing on that. But at the end of the talk, I want to give examples in which this is different and discuss how generally it's done, then that this is always 0. But right now, at least what I want to remark is that there has been a very recent Swampland conjecture, a very nice conjecture by Jeck and Coulomb, precisely claiming that the Bordism group of quantum gravity has to be 0. Because otherwise, if you have here different classes, these different classes can correspond to different conserved global charges, so this would be inconsistent with the common law that there are no global symmetries in quantum gravity. Okay. So in order to avoid the presence of global symmetries, they conjecture that this is 0. And the way you should understand this is that indeed your quantum gravity theory should contain enough defects to guarantee triviality of this Bordism group. Even if it was just, if this was formulated in terms of global symmetries, I think a very nice consequence of this conjecture is indeed that there is no topological obstruction to construct bubbles of nothing in quantum gravity. Precisely because this group is always 0. But of course, it could be that in order to see the triviality of this Bordism group, you need to require, you need to include UV stringy defects or other things. And maybe sometimes we don't even know what is what you need to include. So for this reason, we are going to focus on this example in which we know it's already 0. Okay, we have omega 3 spin is 0. And this way, since we don't need, this is 0 already at the supergravity level, so we don't need to include UV stringy defects, branes, or anything. And this way, we can construct a smooth solution supergravity level so that we can trust the semi-classical regime, so we can have a semi-classical instability and all the formalism for the Phantom solution. And then be confident that indeed we can construct a bubble as a proof of principle. At least we can construct a bubble solution explicitly, even if we have a manifold that has boundary conditions that preserve supersymmetry. Okay. So I'm going to focus now on this particular group. Okay. And this implies that, as I said, any 3-dimensional spin manifold admits a bubble of nothing. And this includes, for example, T3 with supersymmetry preserving boundary conditions. So This should bother you, and I think it's already bothering to some of you, and there has already been questions about it, because what does it mean that? I mean, we know that we can have a vacuum that is supersymmetric, no? For T3 compactification. And a supersymmetric vacuum should not be able to decay. So if there is no topological obstruction, what is preventing the supersymmetric vacuum from decaying? Okay. And well, the answer is energetics. So it might be not energetically favorable to decay. I mean, even if it's allowed topologically, it could be that, I mean, it's not energetically favorable. So recall that we are trying to construct an instability, a decay from the vacuum to nothing. And the vacuum has zero energy, we are in Minkowski. So it will only be energetically favorable if there is another solution which has zero energy or less, right? So this nothing, I mean, in order to construct this bubble, we need to have some solution which is asymptotically flat, so it can interpolate, no? It can describe a decay from the vacuum, but has also zero energy, and that it's different from the vacuum itself. Otherwise, what happens is that when we try now to construct a solution in the sense of solving the equation of motion and get a metric for this manifold, for this Bordism, then what happens is that the only solution, it will have a radius which is infinite. So I will have, in fact, a straight domain wall, and it's not a bubble that is expanding, which implies that the decay rate goes to zero. Okay, this is what is usually known as the Coleman-de-Lucia suppression. But this is very interesting, because if this is all you have, then you can expect that in the moment in which the vacuum breaks supersymmetry, you can get a finite value for this radius. And this is what we investigate in this paper. Okay, so whether this will happen or not, I mean, whether this radius will become finite once we break supersymmetry, it depends on whether, as I said, we can find a asymptotically flat solution with zero alien mass. And this is something that has been constrained by the positive energy theorem of Witten. Is there any other question before I get into this? Okay, so the positive energy theorem of Witten precisely tells us that any solution of this type will have an ADM mass positive energy. I mean, if it's not the vacuum itself, if these both conditions are satisfied. So if the manifold admits asymptotically covariant constant spinors, so we have these boundary conditions that are periodic, no, and consistent with supersymmetry, and the matter content satisfies the dominant energy condition. So this is where the theory matters, I mean, where the field content matters. Because if we want to construct a bubble of nothing in a theory with boundary conditions that preserve supersymmetry, then the only way to avoid this dynamical obstruction is to violate this dominant energy condition. Okay, so the thing is that the dominant energy condition is generically violated once supersymmetry is broken. It's not something very robust. And in fact, I mean, we know it's broken by quantum effects, Casimir energies, higher derivative terms. So I don't have a theorem or a proof that this will always happen, but for sure, I mean, it's something very generic. And what we will do is to include some higher derivative terms precisely to break supersymmetry and violate the dominant energy condition and construct the bubble of nothing. Okay, so this is a summary of all this discussion at the moment, up to now. So given your compact manifold, your favorite compactification, the first thing, I mean, the recipe to check whether you will have a bubble of nothing or not, is that first you have to check if it's trivial in Bordism, okay? Whatever is the Bordism group that matters, that is relevant in that compactification. If it's non-trivial, then there is no bubble of nothing, okay? There is a topological obstruction. If it's trivial, then you have to ask whether they are covariantly constant spin. If not, then you have a bubble of nothing. If yes, then you need to violate the dominant energy condition to get a bubble of nothing. So this is what we call the topological obstruction, and this is what we call the dynamical obstruction, to violate this, no? Preserve or violate this local energy condition. Okay, any question?
Question. In the case when MADM is non-zero far away, as in the positive condition, how much of this is similar to the no soliton theorem in GR?
The no soliton. Well, yeah, you mean because there you also check whether all the solutions have positive ADM mass, or what do you mean exactly?
So there's a theorem in GR that you shouldn't have localized configuration with finite energy, which are asymptotically flat. More recently, yeah. So how does this compare to this? Because the bubble of nothing, in a sense, if there is an MADM is non-zero, should fit in that class. So how does this compare to these statements there?
I mean, the bubble of nothing needs to have ADM equals 0. Exactly, that's the point. But indeed, the theorem, I mean, it seems this positive energy theorem, right? Like that if you don't, I mean, the thing is that in GR, if I just have Einstein gravity, yeah, at classical level, you preserve this dominant energy condition. So if you also have covariant constant spinors, then you can show that any solution will always have a positive ADM mass.
Can I comment?
Yes, sure.
So I have a comment, which is the no soliton theorem assumes time independent. This is a time dependent situation. Once you go to Lorentzian signature.
Yeah, but then, I mean, we also construct Euclidean solutions. I mean, you mean time, okay, not in the sense of Euclidean Lorentzian. Or, I mean, in the end, here you can think of this theorem in Lorentzian. It's true, this is in Lorentzian signature, not in Euclidean. But, I mean, you can just think, I mean, whether, in the end, I mean, later on, what we will do is to construct the Euclidean solution, but in order for the Euclidean solutions to exist, I mean, we need to have this endpoint, no? This Lorentzian solution, which is this Minkowski with a hole that is different from the vacuum itself. And that's why it's constrained by this positive energy theorem.
Yeah, so I mean, I think there's no soliton theorem, I think, does depend upon metric signature.
Okay.
For example, just a simple example, if you take R times T3 mod out by Z2 to give a local description, then the asymptotic will be T3.
Mm-hmm.
And at R equal to 0, it's a localized defect.
Yeah.
So that's in the Euclidean signature, there's no problem here.
Yes, okay, yeah, thank you.
I have another small question. How do I interpret the arrows that says no on the right of the diagram? It means that the solution exists, or it means that you can try to construct it, and it is not.
Okay, yeah, very good. I was going to say now. So, I mean, to be completely clear, these are necessary conditions of the bubble of nothing, no? To avoid the obstructions. So, I mean, to avoid this positive energy theorem. But it's not clear, or it's not proven whether they are sufficient. So, I mean, whether you really have the bubble of nothing. I think they are sufficient, but I mean, this is something we want to study more in the future. I mean, we don't know yet. And what we do, at least in this first paper, is to construct an explicit solution. I mean, to show that once we violate this, then we will be able to construct a solution indeed, and there is no further obstruction, at least here. So that this map works. But it's certainly, I mean, I think it's very interesting. Try to improve this and really try to prove somehow whether these are sufficient and not just necessary conditions. But at the moment, I cannot think of any other obstruction. I mean, what could go wrong? Okay. Any other question? Okay, good. So let's do it. Let's construct a solution to see that all these ideas work, right? In an explicit example. So The example that we took is this T3 with supersymmetric boundary conditions. And we are going to violate the dominant energy condition and break supersymmetry by introducing a Gauss-Bonnet term, okay, this higher derivative correction. Later on, I will show that it is a consistent truncation from string theory, but at the moment, let me just take it as a field theory model. And we have just this Lagrangian, and we'll construct a bubble of nothing here. So I will explain this step by step. Okay, so first of all, the topology of this bubble of nothing. So we said that we have a bubble of nothing if the T3 can be understood as the boundary of another manifold. So what is this manifold for the case of T3, right? For the circle, it's very easy because it's just the disk. But what is for T3? So the answer is that it's half a K3. This was already known, but there is I think there is an intuitive argument to understand why it's like this. So if you have a K3, there is a stable degeneration limit, which becomes like the 2 dp9, 2 dp9s. And if we cut the tube, in fact, here what we have is a T3. Okay. So for simplicity, I mean, in order to construct a solution, we choose that this half K3, okay, this K3 is going to be elliptical fiber. And then our manifold before is then going to have 12 degeneration points. So the fiber is going to shrink at 12 points that we will have to take care of. Okay. Okay, let me also mention that in the paper, we also generalize the construction to find Bordism, not only for T3, but for all the 27 classes of non-supersymmetric flat free manifolds that are constructed as quotient, really acting quotients of T3. And this is interesting because, in fact, last year in this paper, Bobby Archaya was asking the same question as us, whether any non-supersymmetric vacuum is always unstable. And he took these 27 classes and tried to construct a bubble of nothing for all of them. But he was only able to find a bubble of nothing using Witten's construction for 26 of them. And one of them was missing, precisely because the one that was missing is the one that was consistent with periodic boundary conditions. So with the construction that we have, now we can find bubbles of nothing for all of them, including the one that was missing. Okay, so this is the field theory model that we have. We just have the dilaton, Einstein gravity, and this Gauss-Bonnet term. In fact, to start with, we'll put the flux to 0. And the goal is to find just a solution, right, to the Einstein equation on this bubble of nothing, on this Bordism, this geometry, such that it's asymptotically flat, right? That it can interpolate between the vacuum, so the sphere times the T3 at infinity, and nothing, and the bubble geometry at small radius. So this is what took us a lot of time to do. It's really not easy, precisely because to find metrics in K3 is not easy. What we did, in fact, is to find an approximate metric for K3. So we constructed the bubble of nothing by layers. We have different layers, and what we do is to solve the equation of motion separately for each layer, and then glue them together using some matching conditions to any given order in a consistent perturbative expansion. So the different layers that we have are there precisely because we have these degeneration points. So this picture here is like the equivalent of this cigar of Witten. It's just that instead of just a circle that is shrinking, when we get closer to the tip, we have to take care of all these degeneration points to have a smooth solution at the end. So what happens is that we have the T3 at infinity, right? That we take to be a T2 elliptical fiber of the S1. And then as we get closer, so here one can, I mean, the volume of this T3 is large, but as we get closer, then the volume of the fiber becomes small. And then there is a regime in which we have this is the semi-flat regime, in which is still the effect of, we are very far from the generation points, so we can assume that this metric in the fiber is flat. And then, but then if we get closer to the generation point, that this semi-flat regime breaks down, and we enter into this hyperkähler regime. We have this tau nut space, which one cycle becomes small and the other becomes large, and we have to take into account the effect of the KK monopoles to find in the end a smooth solution. Yes, we know that it's the KK monopole. So here we are using a tau nut metric. Here we are using the semi-flat metric. And here, what we do is to solve it numerically in order to connect it asymptotically with the vacuum. And once we have this, for the supersymmetric solution, what we do is to add the Gauss-Bonnet term. And the Gauss-Bonnet term is modifying this solution, but the effect of the Gauss-Bonnet term, I mean, we will consider that alpha prime is very small. So we can work in a perturbative expansion. And what we will do is to solve it to first order in alpha prime, okay, in this perturbative expansion. So to this first order, the effect of the Gauss-Bonnet term is relevant only here in the KK monopole core. And then it propagates back to the other layers by the gluing conditions, and therefore modifies the asymptotic such that the radius of the bubble is finite. Okay, so long story short, we do all this procedure. You can find in the paper, I mean, if you want to see the specific metrics and all the details. And we managed to construct a bubble of nothing for T3 with supersymmetric preserving boundary conditions when we have this Gauss-Bonnet term. And we compute the instanton action in this case and the radius of the bubble. Okay. So as you can see, the bubble of nothing that has a finite radius and a finite decay rate. And just writing this trigger, just because there is some order one factor, it's a bit annoying to write, but it's determined numerically. And we have it in the paper. I mean, it was just to simplify the slide, but you can determine everything. And in fact, it's interesting that for the T3, to first order in alpha prime, there are some moduli, I mean, which remain moduli in standard formations that don't get any potential or anything. So we have sort of a family of bubble of nothing solutions. But I mean, probably they will be lifted once we go to higher orders in alpha prime.
Question in chat, what's D here?
D?
D as in dog.
Sorry, yes, the dimension. So here we are considering a compactification from D dimensions on T3, and it's the total dimension. So in the end, in space-time, we'll have a D-4 sphere. Yeah, the space-time dimension. Okay, any other question? Okay, so as you can see, there is, I mean, in the moment in which we send alpha prime to 0, which means that we turn off this Gauss-Bonnet term, then the radius of the bubble goes to infinity, and the instanton action as well, which means that the decay rate goes to 0. So indeed, this is the Coleman-de suppression that I was talking about, right? That when we restore supersymmetry, then the radius of the bubble becomes infinite and there is no decay. But in the moment in which this alpha prime is non-zero, I mean, this Gauss-Bonnet term is there, even if it's very small, then we will have an instability. Another thing we do is that we construct not just this instanton solution, but we construct an infinite family of solutions with negative ADM mass. And this is important because here, I mean, we are constructing this solution in this perturbative approach, right? So we just solve it to first order in alpha prime. And I mean, we give the prescription how to go to higher orders in a consistent way. But I mean, by going to higher orders, maybe, I don't know, one could say, oh, how you know that this solution is not changing? And then the conclusions are changing. And the thing is that we can construct an infinite family solution with negative ADM mass. So even if this solution with 0 ADM mass changes a little bit, there will be an instability for sure, because the Hamiltonian is not bounded from below. So that's why, thanks to this, we can be confident that there is an instability. Okay. Okay, so now this is the end of the construction. I will discuss about the string embedding and generalization. So if there is any further question, it's also the moment to ask. Okay, if not, then let me say that this is the field theory model that we studied, but we checked also that is a consistent truncation coming from string theory. For example, from heterotic 24 times T3. And we do this just to be confident that we are adding this Gauss-Bonnet term and that this is fine. I mean, it's not that, no, maybe we are getting the bubble because we are adding something strange and we are violating the dominant condition, but in general, you cannot do that. Or, I mean, to show that indeed there are consistent truncations of string theory that violate this dominant energy condition. Now, there is something interesting that happens when you consider the string embedding, which is that there is a Bianchi identity that is relating the H flux and this Gauss-Bonnet term. So if we have a non-vanishing Gauss-Bonnet term, this is turning on also some flux. Okay? And in fact, what happens is that then T3 has a non-SUSY flux. So this flux is the responsible of breaking supersymmetry. Now, still, one can show that to first order in alpha prime, this H will not change the equation of motion, so our bubble solution still embeds here. Okay. But it's interesting that here, as I was saying before, precisely because of this Bianchi identity, we can eat the flux with the geometry, not just with the Gauss-Bonnet term, and we don't need to introduce any pain to have a solution. Okay, we also discussed the embedding in type 1 and the T2Rs to type 2B. And in that case, the flux that is induced is an imaginary dual 2,1 plus anti-imaginary dual 1,2 flux. And this second part breaks supersymmetry. So again, it's consistent that we have a bubble of nothing when we are breaking supersymmetry. As a comment, I want to point out that this type of flux is precisely the flux that is induced when we have a Gugino condensate. So that when we have a KKLT or large volume scenario. Now, we don't know yet whether our bubble solution or something similar to our bubble solution will be able to embed in these scenarios, because here you have also the ingredients, you have 3,0 flux, so there are more things that we will need to add. But there is a chance that indeed something very similar to our bubble could describe a bubble instability in the large volume scenario, which is not known yet what is the stability there, because the vacuum in ADS before the uplifting is not supersymmetric. And then if this bubble of nothing also exists in the KKLT scenario, that would be weird, because in the ADS vacuum in KKLT before uplifting is supersymmetric. So you should not have any bubble of nothing. So probably what happens is that when we try to embed our bubble, maybe, I don't know, because of the other ingredients, in the end there's a dynamical obstruction and something goes wrong and there is no bubble. We don't know. But it could also be that indeed the bubble also exists here because we have this flux. And then that would mean that there is something consistent with the KKLT vacuum itself, because it cannot be supersymmetric and have an instability. So I think it's interesting that bubbles of nothing maybe can also help to hint whether there are inconsistencies in some field theory models, no? Whether they are come from a top-down construction of string theory or not. But it's just a comment. We don't know yet whether this will happen or not. Any question? Okay, so in the remaining time, I want to discuss how to generalize this and construct more bubbles of nothing. So what happens if we add fluxes, charge fermions, and other things, okay? Okay, so in general, first you have to check if there is a topological obstruction. So you have to find out what is the corresponding Bordism group and whether your favorite manifold is in the trivial class of this Bordism group or not. So here, it matters what is the spin structure that we have for the fermions, and it matters if we have fluxes, for example. Okay. So to give some examples, if we have fermions that are charged under a U1, for example, then we have to consider a spin C, obviously. And if we have fluxes, then we have to include here this classifying space of fluxes. So for example, in the string embedding in heterotic string theory that I was talking about, where we have the T3 with H flux, the actual Bordism group that matters, in fact, was not just omega 3 spin, but omega 3 spin with this classifying space. But since we had the Bianchi identity also, this is modifying, like what is the Bordism group that is relevant, and actually the Bordism group that was to check this omega 3 string. And we checked in the paper that indeed our manifold, our bubble of nothing, belongs to the trivial class of this Bordism group. So that's why we were able to construct a bubble of nothing in this string embedding as well. Okay. Now, once you check if there is a topological obstruction or not, the next thing is to check if there is a dynamical obstruction. So you need to overcome this positive energy theorem, either by not having covalently constant spinors or breaking supersymmetry explicitly, or violating a local energy condition. Okay. So the question now is which one, okay? What local energy condition you should consider. In the same way that the Bordism group gets modified, we have further ingredients, also the local energy condition that we might need to check can be different. You have a different spin structure. So the Witten's positive energy theorem actually uses neutral fermions, so we need to extend it in general. And the thing is that if they are neutral fermions, then what you need to violate is the dominant energy condition. But if we have charged fermions, then what you need to violate to have the bubble of nothing is this modified energy condition that we also study in the paper. And this is interesting because when we write it, this modified energy condition this way also, it looks very similar to the weak gravity conjecture. Why is this? It's because, well, for two reasons. First, because in this paper, it was indeed constructed a bubble of nothing with supersymmetric boundary conditions because there was an H field. And what they were doing precisely was to violate this energy condition, even if they didn't phrase it this way. And the way they phrase it is that they were violating a BPS bound, and that's why they had the bubble of nothing. But in the end, this BPS bound is just equal to this energy condition. And the weak gravity conjecture is sort of an anti-BPS bound. And in this other paper, in fact, I mean, it was computed what is this modified energy condition, and it was used to show that any solution, asymptotically flat, has positive ADM mass. Sorry, not positive, so has an ADM mass which is bigger than the charge. So it was used to show that black holes that have a mass bigger than the charge, this BPS bound. And we would expect that precisely a theory that preserves the weak gravity conjecture, so that has particles with a mass smaller than the charge, is probably going to violate this modified energy condition. But this is something that we just point out, and we would need to study much more in the future, whether there is really a one-to-one correspondence between both of them. Okay, any other question? Okay, so this is the recipe. Let me come back to the recipe now a bit more general. So given your manifold with whatever structure you have, you need to check whether it's trivial in this Bordism group. If not, you don't have a bubble of nothing because you have a topological obstruction. If yes, then you need to check if it has covalently constant spinors. And if it has it, so the boundary conditions are consistent with supersymmetry, then you need to violate the relevant energy condition that applies in that case in order to be able to construct a bubble of nothing. As I said, so this is topological dynamical. As I said, this has been conjectured to be always trivial in this Swampland conjecture. And anyway, we know many examples in which it's really trivial, and we could start constructing many more bubbles. And this other one, I mean, we discussed that the dominant energy condition is generically violated. Once we have fluxes, what we have is this modified energy condition, but it might be related to the weak gravity conjecture. So maybe indeed, in quantum gravity, it's also always violated. That would be like the next step to check. And I think it's interesting the analogy here with the Swampland, because in the same way that this Swampland conjecture was based on the absence of global symmetries, it might be that the absence of a dynamical obstruction, then it's related to these other conjectures which try to quantify how close you can get to restoring a global symmetry. So they talk about the dynamics, right? So the topological obstruction is more about the global symmetries, and the dynamical obstruction might be related to these other ones. But just a comment. And if it happens that indeed this Bordism group is always trivial, and that this energy condition is always violated, then bubbles of nothing would be a universal instability of quantum gravity every time supersymmetry is broken. Okay. So this is actually my last slide. I just wanted to point out that there's a lot of recent activity in the Swampland program, and I will give some lectures next week. And I think one of the most interesting things is all the relations that are appearing between the different conjectures. And I think with this paper, we are pointing out, if you want, another connection between the fact that this trivial Bordism group, this Bordism group is trivial, and the non-supersymmetry buffer are unstable. But it would be interesting to understand much better this dynamical obstruction. Okay, so let me summarize. So bubbles of nothing are far more common than what we thought, at least what I thought, because topological and dynamical obstruction are typically absent in quantum gravity. So that's why the title of our paper, that nothing is certain in string compactifications. And as a proof of principle, what we do is to generalize this Witten's bubble of nothing and construct a solution for T3, even if it has supersymmetry preserving boundary condition, by adding a Gauss-bounded term and breaking supersymmetry in the vacuum. But I think the most exciting thing is that this is only the beginning, because we can construct many more bubbles of nothing. There are many other cases in which this Bordism group vanishes, and we can try to construct the bubbles of nothing and try to find out whether they will always be there, and whether it's really enough to violate these local energy conditions to have the instability. So thank you very much, and let me ask if there are more questions.
I have a question. Very nice talk, Irene. Are there cases where the bubble of nothing is the primary mode of decay, in the sense that typically when you have non-supersymmetric ones, you will have other effects which are much stronger than these non-perturbative effects you're describing? Are there cases that you can specifically say has to be this way?
Yeah, that's a great question. So it's true. In general, there are other instabilities. Once you have the bubble of nothing, maybe, and if you have fluxes, usually, the usual Coleman-de-Lucia is more likely, so the decay rate will be faster. I only knew some examples in ADS, that there was some ADS, examples in which there was no known instability, and then it was found a bubble of nothing. Like, for example, Hiroshi in his paper of ADS with CP3. In that case, there was no known instability, and the bubble of nothing seemed to be the only one. But we also learned recently that even in that case, it seems that there are some fields that saturate the BF bound. So maybe by going to higher orders, actually they describe an instability as well. So, yes, exactly.
Yeah, that's what I would expect. I would have expected there are always perturbative instabilities. To kill all the non-perturbative, to kill all the perturbative instabilities in a non-supersymmetric theory of quantum gravity requires infinitely many fine-tuning, which is not available. So I would think that it's hard to believe that there is no instability before we get to bubbles.
It could very well be that in the end there is always another instability. This was the only case I knew, but it seems they saturate the BF bound, so it's a bit, maybe it's an instability in the end. And I think that would be very interesting, because then it means that, exactly, even if the bubble of nothing are very highly suppressed, you will have another instability which is much faster. Why I like the bubble of nothing is just because I find easier maybe that we could show this as a universal instability, or try to prove that it's
right. That's the last resort, so to speak.
Yeah, it's much more suppressed, but maybe it's easier to ask, for generality. While
Yes,
the other ones are more model dependent, whether you have a tachyonic direction, right, this particular instability.
Regarding the absence of perturbative instabilities, what is the status of the skew-wift solutions? I think those don't have any.
Sorry, which ones again?
The skew-wift solutions, which are those which where you take a supersymmetric solution and you just reverse the sign of some flux.
That you're only breaking supersymmetry in the boundary, right?
Yeah,
Like,
that's
yeah, no, this,
In the
there-
what boundary? Sorry.
you don't mean in ADS, or yes?
Yeah. So these are ADS. So you take your favorite ADS solutions with fluxes and you reverse the sign, and you
Yeah.
typically get a non-supersymmetric solution.
Yeah, I don't know. That's something we want. In fact, we were checking now these type of solutions to see if we can construct a bubble there.
The spectrum is still the same, so that's going to be
Yeah, it seems. I agree. It seems difficult. There's also the typical counterexample of Eric Permuter and so on, and Giombi, that they have this double trace deformation, n equals 4, and they are also breaking supersymmetry, but it's sort of.
No, okay, but those are okay. That's a lot more exotic. I also want to point out, if you're interested, that there are compactifications where you can take ADS4 and CP3, for example, and deform it by Romans mass. And in that case, you can, since there are small deformations of solutions that have nothing at the BF bound, where it will no mass that sits exactly at the BF bound. Well, then you can make your deformation very small so that you can prove that there are no perturbative instabilities. Okay. And yet there are no perturbative ones.
Okay, that's interesting.
Sorry, you're saying you can prove there are no perturbative instabilities?
I think so. I mean, you start from a very well-known solution, which is ADS4 and CP3, where you know the spectrum, and it so happens that there is nothing for that solution. There's nothing that sits exactly at the BF bound. There was for the ADS4 and C7 solution, but once you reduce, well, okay. So regarding your argument, so you might say that perhaps looking at the spectrum in ADS4 and so my statement is a supergravity one, okay? Because regarding the so you may say, oh, but you're starting with the ADS4 and CP3. And the spectrum for the ADS4 and CP3 is incomplete because you really should go to M theory.
Right.
You might say that. However, when you deform with the Romans mass, you no longer have a.
Okay, so you don't have any M theory example. If I'm expecting,
So I don't know exactly. So, but if you believe, as I do, that the 2A with the Romans mass has a non-perturbative completion, then.
Okay, so I think if you were conservative, there are no examples. If you're willing to go with Romans mass, there may be examples.
So, if you're conservative, then so you're saying that 2A with the Romans mass is in a swampland.
No, I would say that you would have to understand what it means exactly. We don't know yet.
I'm happy you're not saying that.
And what I want to do also with all these ADS examples is try to take more these dynamical obstructions. Maybe instead of trying to construct an instability, it might be much easier first, like to check if they violate the corresponding energy condition in ADS, which is going to be different than the ones I described. I don't know, maybe one can check whether, I don't know, these ingredients, even if you don't see the instability, whether if you are already violating that condition, and then it's very likely that you will have an instability, even if you don't see it. I didn't mention, for example, it's interesting here that with the Gauss-Bonnet term, we are violating the dominant energy condition, but only if the Gauss-Bonnet term has a particular sign, alpha is positive. But this sign is precisely the one that comes from string theory, and that is consistent with some unitarity constraints. So, yeah, I don't know. I mean, I think it's a way to go. I try to check these energy conditions and try to understand what is the relevant energy condition in each case and how to violate it.
Irene?
Yes.
You could also have Chern-Simons terms in your supergravity, which can actually support these things. What have you guys studied examples with that, and can actually having Chern-Simons terms end up lifting these objects?
Yeah, I mean, so the Chern-Simons terms are going to have a very similar effect that is Bianchi identities, right? Mm-hmm. So that's part of the, okay, this is something in fact we are thinking now, that, I mean, we had, maybe it was wrong our perspective, but we had the perspective that once we have fluxes, probably we need to add always these branes or UV defects or something like that. But then we realized that that's not necessarily the case.
Yeah.
And it's not necessarily the case precisely when they are Chern-Simons terms. Or
that's right.
Bianchi. Exactly. because then you can eat the flux in different ways.
Yes.
So we are precisely checking whether, I mean, and we always have Simon terms in the string theory, right? It's sort of a common feature all the time. So maybe we can try to give some more general argument that precisely when we have these Simon terms, then, I mean, already at the supergravity level, we will always have these bubbles of nothing because we can eat the flux that way and there is no topological obstruction. But it's a very interesting remark. I mean, we have to study more of that.
Thank you.
Are there any other questions?
Maybe I do have one, but I'm afraid it's a stupid one. So I got a bit lost. So the moment you had the written, you have shown that T3 is a boundary of the del pezzo 9.
Half a K3, yeah.
So wasn't your job basically over? Why? So I mean, topologically, I understand that then. Okay, good. Yeah. So then the next, so at some point, okay, you go in, and then at some point you say, oh, there's a hyperkähler region, and here I use the Taub-NUT. Okay, so then, okay, with the Taub-NUT ansatz, I can find a hyperkähler solution with those with various nuts. So then, why do you need the further zoom? That's where I got.
Well, it's just to get to the tip. I mean, to show that this. I mean, we already. It's true. It's known that it's a smooth solution. Not is smooth, but we get to the tip because in the end, what we do is to deform everything by adding the Gauss-Bonnet term. So we have to modify these metrics. I mean.
No, but that's precisely where I got confused. I understand that you want to have the Gauss-Bonnet term because you expect that the dominant energy condition should be violated. But why do you need it in the equations? I mean, to actually find the metric.
No, so we have a metric without the Gauss-Bonnet term, and it's the supersymmetric metric. And it's not describing a bubble because what happens is that when we try to paste it, to glue it with the asymptotics, it doesn't glue with the T3, with the vacuum, because it has the radius is infinite, so it doesn't have a finite radius for the bubble. It's not asymptotically flat, the solution of finite radius. So we need to modify it in order to be able to glue it with the vacuum by keeping a finite radius. And that's why then we introduce the Gauss-Bonnet term and then modify everything so that in the end, the warping in the end is non-constant. I mean, it's not one. And we can have a finite radius that can interpolate between the T3 and the vacuum and nothing. Yeah.
Thank you.
Are there any other questions? Well, if not, let's thank Irene again for the wonderful talk.
Thank you.
And I guess we'll turn off the recording now. And if people want to stay for a bit and chat or ask questions offline, feel free for a bit. I think the organizers will go into